Welcome to the final webinar in the 2025 Earth Science Week webinar series. Today's topic on geologic mapping and modeling features a number of speakers who will speak about the value and uses of geologic maps. Geologic Map Day occurs annually on the Friday of Earth Science Week and is hosted by a number of geoscience organizations in partnership with the American Geosciences Institute. In this webinar, we want to share resources with you that you can use to celebrate Geologic Map Day this year and in the future. As part of the annual Geologic Map Day celebration, we at AGI create a Geologic Map Day poster that can be used in classrooms and at outreach events. The Geologic Map Day page highlights this year's poster, which shows the new Cooperative National Geologic Map created by the U.S. Geological Survey, and which is the focus of today's webinar. This page also includes last year's Geologic Map Day poster of the moon, as well as a number of activities relating to the use of geologic maps, from locating geologic hazards to exploration for energy and other natural resources. For more on the benefits and uses of geologic maps, let's hear from Chris Keene, the Director of Geoscience Profession and Higher Education at the American Geosciences Institute.
Every road we drive, every building we build, every drop of water we drink, all of it depends on what is beneath our feet. Geologic maps are our window into the planet. They turn collections of data and observations into a powerful knowledge product, a synthesis that is far greater than the sums of its parts that powers critical decisions that makes the society we live in. A geologic map is more than a colorful piece of science-driven art. It is a result of years of observation, measurement, and interpretation by geoscientists. It shows the distribution of rock types, structures like faults and synclines, gives us key insights into resources such as groundwater aquifers, minerals, or energy like geothermal, and the conditions that can become natural hazards. It transforms raw data into insight, gives us a clear, usable picture of the Earth's structure and history. Geologic maps are essential tools for a wide range of professionals. Environmental scientists use them to plan projects to protect the environment, groundwater, lakes, and rivers, as well as to remediate polluted sites. Mining and energy industries rely on them to identify places to find and develop resources responsibly. Construction and civil engineers use them to avoid costly surprises when building roads, bridges, and tunnels. Real estate developers are, from an economic impact, the single biggest user of geologic maps, as they depend on them to evaluate land suitability and risks, including key issues such as flooding, land stability, and radon. Finance and insurance sectors use geologic maps to assess natural hazard risk, from earthquakes to landslides. Policymakers use them to guide land use planning and hazard mitigation. And it doesn't stop there. Hikers, fossil and mineral hunters, educators, and photographers all turn to geologic maps to explore and appreciate the world around them. Several studies have shown that geologic maps deliver a strong return on investment, often many times the cost of creating them. By preventing construction delays, guiding resource development, and reducing disaster losses, they pay back society many times over. Most geologic maps in the United States are produced by the U.S. Geological Survey and the individual state geological surveys. A 2018 study of geologic map users found that their products were considered the gold standard, with 99% of users viewing them as extremely reliable, compared to privately developed maps, which have a 40% reliability view. In the 2025 report Economic Analysis of the Costs and Benefits of Geologic Mapping in the United States of America from 1994 to 2019, the specifics of the impacts become clear. Most importantly, these publicly funded geologic maps are a public good, which means they are non-rival, that by using the map, you are not reducing the value to another user, and that they are highly accessible to all people, especially using the U.S. National Geologic Map Database website. This has turned the $1.99 billion investment between 1994 and 2019 into an economic activity of at least $20.6 billion. They are a form of public infrastructure, intellectual infrastructure, that quietly supports our economy and safety every day and powers real economic growth and associated jobs for the United States. Geologic maps are living products. As new data is collected, from fieldwork, satellites, drones, and sensors, they evolve. With the maps now digital, they have become dynamic and steadily increasing their value. This constant refinement means they get better over time, integrating decades of accumulated knowledge. In a world of change in land use and hazards, increased critical mineral demand, and infrastructure and renewal, Up-to-date geologic maps are more important than ever. Geologic maps are the foundation for wise decisions about our land, resources, and safety. They're an investment in resilience, economic growth, and discovery. Whether you are building a bridge, protecting a watershed, or just planning your next hike, geologic maps help us see the Earth clearly so we can shape a better future.
The next segment of this webinar features three speakers who are experts in geologic mapping with the U.S. Geological Survey, a longtime partner of Geologic Map Day and Earth Science Week.
Welcome to the Cooperative National Geologic Map webinar hosted by the American Geosciences Institute. My name is Joe Colgan with the USGS. I'll be giving an introduction to geologic maps. My colleague Sam Johnstone will talk about how we built the new Cooperative National Geologic Map, and then we'll have a demo of the beautiful web application from our colleagues Chris Garrity and Rob Wardwell. So what is a geologic map? A geologic map depicts the distribution of Earth materials and the relationships between them. The colored areas on these maps indicate different types of rocks or sediments. Depending on the map, these can be highly specific things or broad groups of things that have some similarity to each other depending on the purpose of the map. The lines on these maps show how these materials are related to each other, like these thin contact lines here. This tells you that this pink unit was deposited on top of the blue unit here. And heavier lines, for example, indicate faults, places where rocks were juxtaposed with one another after they formed by deformation of the Earth's crust. Point symbols on these maps tell you about observations that were collected by geologists, like these sample localities here with the sample numbers, and these strike and dip symbols that tell you about the orientation of geologic features like bedding in space. Geology on these maps is depicted on a base map, often a topographic map. They can also be on satellite images, shaded relief maps, things like that. The USGS 1 to 24,000 topographic maps have long been a very popular choice as a geologic base map, so you'll see a lot of geologic maps based on those. Why do we make geologic maps? What good are they? Well, the AGI just put out a great report on the economic benefits of geologic mapping that has a lot of great information in it about the kinds of things geologic maps are used for and the economic benefits that they provide to society. I like this quote early on about how geologic maps provide a scientific foundation for all modern societies. They tell us about the origin and distribution of resources we need, like minerals and water and energy, about geologic hazards like landslides and floods and earthquakes, and I'll throw volcanoes in there for my USGS colleagues. They're a primary source of information for any kind of land use planning, the siting of roads and bridges and buildings and landfills, aggregate resources for construction, those kinds of things. And finally, for resolving fundamental scientific research questions about the evolution of the Earth and its physical environment. I'll talk a little bit about two different ways that geologic maps can get made. The first is a map made in the field. This is where a geologist goes out and walks around in the mountains or on the ground looking at outcrops and sediment and whatever they can, and recording observations on their geologic base map as they go, drawing lines around the units and point observations and so forth. There's me looking at a rock with a hand lens to figure out what's in it, taking some notes on what I saw. This used to be done with pens and paper. Here's an old field map of mine from when I went to geologic mapping school, where you drew lines with pencils as you went in the fields and came back to camp at night and traced over them with ink and colored pencils, and I loved this aspect of it. But like a lot of things, it is now done mostly digitally. But the principle is the same of a geologist going into the field and collecting the observations to fill out the map as they cover the ground. A different way that geologic maps get made are compilation maps, where a geologist in the office takes data from many field maps and synthesizes that into a single map, usually at a reduced scale. So for example, compiling a bunch of 24K maps that were made in the field into a single 1 to 100,000 scale map. In doing this, the person making the map, the lead compiler, decides on a set of compilation units for the new map and which source units from the original map belong in each one. So let's say your 24K maps had 200 different units on all of them, and you only wanted 40 for your compilation map, so you have to decide what those 40 are and where each of your 200 source maps units go among those 40 compilation units. There's no specific formula for this. It really just depends on the interests of the person doing the compilation and what the purpose of it is, what the scale is, and what they have to work with from the source maps. So once you have that worked out, you draw lines around the new units, simplifying them for the reduced scale as you go. This used to be done, on light tables with pieces of transparent mylar, green lines, and tracing over things with pens. But nowadays it's done on computers also using GIS software. But the idea is the same of somebody making decisions about how the compilation is going to get made, simplifying all the units and organizing everything according to some scientific principle. So let's talk about some different styles of geologic maps. Different parts of the United States have different geology. Of course they do, even down to the level of individual quadrangles or areas. Everywhere is a little bit different. A major and profound division with respect to geologic mapping, though, is between the area covered by glaciers during the last ice age and the area that wasn't. So this blue line here on this map is the extent of the ice that came down during the last ice age. This area above it was covered by deposits left by those glaciers. In that area, geologists tend to map those deposits, sort of yellow in this cross section, on a separate map, and then map the bedrock underneath on a different map. And in some places, they make a third map of the basement rocks that are way down underneath that. On the other hand, areas in the southeast, and especially the mountains out west, are not well layered, or they have layers that got mixed up by faulting and folding when the Earth's crust was deformed. And so there we usually make a single layer map showing everything exposed at the Earth's surface, sort of regardless if it's, young sand in a river or some kind of ancient bedrock. Here are some different views taken from the new National Geologic Map of some of these different styles of mapping. This top set of panels is from southeastern Minnesota. My old hometown of Rochester is there with the star. And the state of Minnesota has made a quaternary map. Those are the glacial deposits mostly. They've made a bedrock map of rocks older than quaternary, which in this case are mostly Paleozoic carbonates and sandstones, and a map of the basement that's down under that, Precambrian crystalline rocks that are very old. On the lower left, on the other hand, is an example of a single layer map from out west. This is from Colorado, where I live now, and Golden is right there. And you can see this map shows everything from the young sediments along the South Platte River here in Denver to 1.7 billion year old granites and metamorphic rocks in the Rocky Mountains over here west of town. So these are the 4 layers that you have the option of choosing when you look at the new national map. The USGS has been making national geologic maps for a long time, almost since it was founded. We were founded in 1879 and came out with our first national geologic map in 1885 by McGee, a preliminary version, and then the final version of that he put out in 1893, and that's the version that you see on this slide. It has 12 geologic map units for the whole country, so pretty generalized. Large parts of the West are blank because they hadn't been surveyed yet. But overall, like the rest of it, looks pretty recognizable. Here's the Appalachians, Paleozoic basins in the mid-continent, all the young deposits, Mississippi embayment and the Gulf Coast. You can see the Rocky Mountains starting to get filled in. And you'll notice that they included the youngest quaternary deposits along the coast here in the Mississippi embayment, but left them off in the area where they were deposited by glaciers choosing instead to depict the bedrock underneath. There's that kind of dark overlay pattern that shows where the glacial deposits were. And so it's kind of a hybrid map that shows what's at the Earth's surface in this area and what's underground up in this area. And that precedent has been followed by all subsequent National Geologic Maps. There was another one in the early 1930s, and then the King and Beichmann 2.5 million scale map in 1974. Then in 2005, Jack Reed and others put out the 1 to 5 million scale geologic map of North America. So it's less detailed than the King map, but more recent. And that was the first geologic map to include both Alaska and the 48 states on the same map. And those two maps remain the sort of most up-to-date maps if you want a traditional, kind of hand compiled with a nice cartographic layout geologic map of the United States. So there's also been, for the last 3 decades or so, kind of a parallel strand of geologic map compilation based on digital data. And this grew out of the recognition in the late 1990s and early 2000s of a real need for more detailed nationwide geologic map coverage than things like the old King map could provide. The USGS is often called upon to do assessments of resources and hazards and other things that require off-the-shelf geologic map data from some region of the country, or sometimes the whole country itself, where there's not time to go make a new map just for that purpose. So the USGS Mineral Resources Program started digitizing individual state geologic maps, mostly in the 1 to 500K scale range, to cover the 48 states with digital data. These started getting released in the early 2000s, and then this culminated in 2017 with release of the State Geologic Map compilation by our colleagues Karma San Juan and John Horton in the Mineral Resources Program. And so this is all of the digital data from these state maps brought together without modifying it, so no redrawing lines or trying to fix busts where maps didn't match across borders. They just brought all the data together in one database, sort of as it was. And you can see a little bit of that here in this view where it's colored by generalized lithology. So, poor North Dakota is just a big brown spot and there's weird busts at the map borders. But having all that data together in one place is enormously useful, and this has become a widely used analysis-ready data set for a lot of purposes, and really showed that you didn't have to go the traditional compilation route to make something extremely useful. So this brings us to the new Cooperative National Geologic Map. Our goal for this was to build on both traditional compilation approaches and digital syntheses like that pioneered by the SGMC. We wanted to deliver a product quickly, so in a few years, that was built to be easily updated as new maps are produced in the future. So we needed to bring together unmodified source maps produced by the USGS and the state geological surveys, who do a lot of the mapping, hence the term cooperative in the title. We wanted to build on what at the time were newly issued standards for digital geologic maps, automate the process of bringing those together. We wanted to include all major styles of map geology nationwide. This is an allusion to a comment by Phil King for his national map that he had no regrets sacrificing the Pleistocene glacial deposits. We would regret it, and we wanted to include them. And finally, we wanted to create views of the data that looked and felt like a traditional USGS geologic map, and you can see the results of that in the beautiful web viewer that we'll get to see at the end. Right now, I'm going to turn this over to my colleague Sam Johnstone to talk about how we actually built the map.
I'm Sam Johnstone from the U.S. Geological Survey in Denver, Colorado. I'm going to be talking today about the most complicated 100-piece puzzle I've ever been a part of assembling. That is the Cooperative National Geologic Map. Unlike past National Geologic Maps, this is not built by a person trying to characterize the nation's geology, but is built by a system seeking to bring together the maps that are produced by geologists across the country. The National Cooperative Geologic Mapping Program has established a standard called GEMS, the Geologic Map Schema, a way of organizing geologic map data that allows individuals who are picking up a modern geologic map to know exactly how to interact with that information in a common way. It also allowed us to build a system that can ingest this data into a single standardized database, and in the process of that ingestion, associate other attributes alongside those maps, referencing information for where the maps came from and attributes that let us associate units with one another. That'll be important later. We can then take those individual maps in that single system and start to stitch them together into this single quilt or puzzle. That's what's in 3 here, where we're piecing together these individual maps. And then, as one of the major innovations of this effort, we've come up with a new way to synthesize and aggregate these individual maps in order to provide an integrated display that looks like a traditional geologic map and can be read like one, but is built in an automated fashion using a system that relies on the attributes derived from the original publications themselves. The advantage of this being driven by an automated system is we can keep repeating it as new maps are produced throughout the country, and there's lots of new mapping that's going on right now. We'll talk a little bit more about that as the talk goes on. What this looks like in practice is continuing to bring pieces into this puzzle, laying things down one at a time in this database system and stitching these things together into this quilt. I've symbolized it here by how these maps were originally published, the cartography that these authors used in order to depict the geology of these states or regions with as much detail as they thought was appropriate to showcase and highlight various aspects of the geology within that region. However, this results in a pretty disjointed looking quilt originally, and we can see that in a little bit more detail by zooming in to the area around 4 corners here. Across these boundaries between these 4 states, we see vastly different applications of color, lines that don't match up with one another. It looks like a pretty different set of geology that's mapped between these things. We have a big accumulation of brown units here that aren't shown in this map of Arizona, different shades of green, some places where things line up, but a lot of places where they don't. And it leaves us sort of wondering how we might actually start to associate this geology. Past national map authors sought to standardize and integrate this to provide a unified view by redrafting the geology, typically at coarser scale, drawing new boundaries between what ended up being coarser groupings of units. This allows for this standardized depiction across the country, generalizing things into often around 100 units that can be read by a user who's looking at an individual map. But it results in less complexity in how those units are describing the geology and less complexity in the spatial distribution of units. What we adopt here in the Cooperative National Geologic Map is this data-driven strategy, where we still seek to provide an integrated view, but we do that with a data-driven strategy rather than one that's reliant on an individual recompiling and redrafting the geology. The goal here was to allow the compilation to evolve at the same pace as new geology and new geologic discoveries are being depicted in individual maps that are published across the U.S. by both the USGS and by the many state geologic surveys that exist around the country. Specifically, what we use are taxonomies of language, something that we're all quite familiar with, but maybe don't put a name to that often. I have here a photo of a bird. It's also a photo of an animal more broadly. It's not just any bird, it's a crow, and it's not just any crow, it's a highly smart crow that's known for its ability to use tools called the New Caledonian crow. We can use these specific or general terms to group things that are like or differentiate things that are dislike and to communicate to different audiences about what things are. I'm probably not going to talk to my 4-year-old about the New Caledonian crow, but she definitely knows crows. We have a very formal taxonomy that many of us who have engaged in geology are familiar with. That is the geologic timescale. this series of intervals that divide up the 4.5 billion years of Earth's history into these named periods of time. They're hierarchical, so we know that the Holocene is part of the Quaternary, is part of the Cenozoic. We can specifically talk about the Mycenian, or we can talk more broadly about the Miocene. If we apply this hierarchy of age back to our original map units, we can start to see some of the associations that exist between these map units. Now we have this broad region of greens and blues. These are rocks from the Mesozoic, think the age of dinosaurs, and most specifically the Cretaceous and Jurassic, where we see similar colors, similar periods of time depicted across these map boundaries, although with different levels of specificity, different hues within these color palettes. And then we can see these orange periods on top of that from the Neogene period, I believe. We can alternatively apply taxonomies of materials, specifically vocabulary that we call geomaterial that comes with every GEMS database. These browns and tans are sedimentary rocks. Yellows are unconsolidated materials recently laid onto Earth's surface, and these pink and purple hues are igneous rocks. What we do in the national synthesis is take this relatively patchwork quilt of disjointed units and just start walking up that taxonomy of language, going from the New Caledonian crows of individual maps to the broader categories of crow by finding those places where there are broad associations of geologic units that are relevant to depicting the history of the country at national resolution. So by intersecting these age and geomaterial taxonomies, we can find this common set of units that is relatively consistent across the US, but still preserves the rich detail of those original units. Zooming in here, the grouping that we saw, and in this case the King and Beekman map, resulted in a relatively simplified depiction of the units, just Lower Jurassic and Upper Triassic. Here, in our synthesis, we can still see these common associations of units, but in these Jurassic sedimentary rocks in our national synthesis, we can see that this individual polygon was described in its source publication as conspicuous red cross-bedded sandstone and Navajo sandstone. And in an adjoining map, we had a little bit less detail and a description of a different formal formation. One of the real reasons that this data-driven approach is valuable is there's a lot of mapping going on across the country. While there were about 100 maps stitched together to make this quilt, there's new mapping that's going on that's going to make much of what we have here out of date in the coming years. What I've depicted here are statewide or multi-state maps that I'm aware of that are being produced as we speak, and I expect to deprecate some of the mapping that we have in this cooperative map when they come out. However, there's a lot more mapping that's going on, and I'm sure I've also missed a couple statewide maps too. So I'd encourage you all to visit your local State Geologic Survey's website, which you can find through the American Association of State Geologists at stategeologists.org. You can also take a look at detailed mapping efforts funded by the National Cooperative Geologic Mapping Program through the National Geologic Map Database's Mapping in Progress site. That's at ngmdb.usgs.gov/MIP. That'll show you both 3D geologic models that are being built of whole states or counties. It'll show you detailed maps people are building in the field and compilations that people are building from those field maps. Because we know all these things are coming out, we wanted to be sure that we built this cooperative map in a way that we could update it relatively easily. We're going to zoom into this region here and show an example of cutting out a region of mapping and relying on this standardized format to be able to ingest a new set of maps and relying on the system to automatically apply the same set of synthesis units. So we have this relatively seamless and efficient process of updating this map as new mapping comes online. This purely data-driven approach, though, does leave map busts, and we hope these will continue to be refined as folks work to produce new geologic maps, and we incorporate them into the system. But we'll also introduce new busts as a result of that when people make new discoveries about the geology that force some new differentiation of units that wasn't recognized in an older map. Here's some of the largest busts that you can see on the map now. These are not reflections that the geology is wrong from one map to another. In a lot of cases, they're just reflections of differences in priorities. The most common difference that I tend to cue in on are differences in the extent of aeolian or wind-blown deposits from the Quaternary, sands and silts that are extremely common across the Great Plains, but tend to thin as we approach the more rugged Rocky Mountains. As a result of that thinning, authors of maps, for example in Colorado, put less emphasis on those Quaternary deposits that blanketed less of their state. It's not wrong to do that. It was just a choice to depict the geology differently in that state based on what was commonly depicted there. However, those Quaternary deposits are extremely important in a lot of parts of the world, particularly in the glaciated regions upstream of this blue line here, which depicts the advance and retreat of glaciers during the Quaternary period as a result of cooling temperatures. We have this vast record of sedimentary deposits that are extremely important for example, aggregate resources and near-surface groundwater flow. As a result, people making maps in those areas tend to make two types of maps, the maps of this Quaternary geology and the maps beneath the surface of the longer record of geology buried under those Quaternary deposits. However, past national maps, like Reed's Geologic Map of North America here, instead simply depicted the extent of these glacial deposits with a line of the limit of glacial advances, where upward of this, we have areas that are intermittently covered by glacial deposits and not so much downstream. We can reproduce that same pre-Quaternary bedrock depiction thanks to the work by those geologists working in state surveys in the USGS to make these pre-Quaternary bedrock maps. And here I've shown a synthesis that resembles that Reed Geologic Map of North America. However, because of the work to also characterize the near-surface geology, we can also show that rich record of the advance and retreat of glaciers recorded in these recent sedimentary deposits that, again, are so important for things like groundwater flow and what's immediately underfoot for people that live in these regions. Now I'm going to walk through a demonstration of the Cooperative National Geologic Map application. This was put together by the team at the National Geologic Map database, particularly Chris Garrity and Rob Wardwell, and Dave Soller is the lead of that map database, which we'll see a lot of resources from throughout this demonstration. What I'm going to do is first hop over to my web browser, navigate to the NGMDB by searching National Geologic Map Database. If you've got a good memory, you can go to ngmdb.usgs.gov. What we're going to look at here is this National Geology tab, but there's a lot of other wonderful references here too. If you want to learn more about a particular geologic formation, you might be interested in the lexicon. What I want to show you right now, because we referenced it earlier, is this new mapping tab, which shows ongoing efforts in the USGS and state geologic surveys to produce new geologic maps and models of the subsurface. If we zoom into a particular area here where we're interested in learning about, let's see, I'm near Denver, so I'm going to zoom into this orange region, click on this polygon, find out more about this new Northern Front Range Piedmont Area Geologic Mapping Project by going to the Colorado Geologic Survey's website by following the link here, which will probably lead me to all sorts of other interesting resources. Hopping back to the NGMDB, let's take a look at what our focus for most of this demo is, again, in this National Geology tab here. When I bring up the Cooperative National Geologic Map application, we start off with kind of two important pieces of information. There's the map in the center part of the panel here, where we're starting off looking at the Earth's surface synthesis map. And then we've got this info bar, which we'll see more about throughout this, and then some buttons at the far left that can provide us more information. The About button just tells you a little bit about how this map came together, what all these symbologies and layers are. The Help button is where you're going to want to go if you get stuck trying to figure out how to interact with something, or you have some questions that perhaps other people have had too. Those might be answered in the frequently asked questions down at the bottom. If you're interested in getting data for this particular map, well, find your way to the Get Data button, where you can download images of the individual maps or the data sets of those maps themselves. What I want you to really pay attention to is the ability to toggle these different layers. So we talked a little bit about the different styles of geologic maps and how we've attempted to replicate that by different layers of maps in this cooperative national map. So here we have the Earth's surface layer. Alternatively, I can tab over to a layer focused on Quaternary geology, that is those rocks that were formed in the last 2.5 million years or so. I can look underneath these glacial deposits, just like Reed and King and Beekman before, by looking at the pre-Quaternary geology to understand the longer history of our country recorded in the deposits buried beneath those glacial tills. Or I can kind of peer into the crust by looking at the Precambrian layer here, which throughout the central part of the U.S. is often inferred from borehole and geophysical data, and it also outcrops in mountain belts in the southwest and in the east. For the remainder of this demonstration, I'm going to focus on the Earth's surface layer, but these same strategies apply across all the layers. If I go to a particular location, well, actually, first let's start to zoom in a little bit slowly to show some of the first initial functionality here. So one of the most basic questions is, well, what am I seeing here? To see what you're seeing, you want to zoom in enough that there's a reasonable number of units to be able to read them, and then you're going to have this legend pop up on the right. The legend will respond to which units you're looking at here or which units are in view. And you can make it simpler by toggling this button to just show the list of units as opposed to their descriptions. The legend will respond to whatever symbology you have to show the full complexity of source units, to characterize just the geologic materials of those units, or to show units by that taxonomy of age. If I zoom in even further here, we start to see line work appear. I'm going to look at that in terms of the synthesis view. These bolder lines are faults, and the different decorations on those faults are symbologies that the geologists use to communicate the style of tectonic motions that have occurred for rocks to slide past one another along those fault planes. There's also lines between the bounding colors here that depict the nature of the contacts between units and how confident geologists were in mapping those. The dashed or question mark faults or contacts are places where faults or contacts were inferred or buried beneath other units. You want to understand the full symbology that's used to depict these lines. We rely on a standard USGS symbology set that you can find by searching for FGDC Geologic Map Standard, which will take you to another NGMDB resource here. Specifically, I like to look at this PostScript format, which lets me look at all the many types of thematic line symbols that are available. I already opened up one of these things for faults in particular, which will show me all the variations on normal faults, thrust faults, reverse faults, etc. that exist in their varying levels of confidence, which are depicted in these maps. If I click on a point, I can get more information about that specific point. At the very top is going to be whatever kind of or whatever attribute you're displaying. We see a few different pieces of information, which are the different symbologies that we have here: the synthesis, the geomaterial, the source, the geologic age. If I switch over to a different symbology, those attributes will be front-loaded in this information panel. If you forget what any of these things are, you can hover these little info buttons for more information about what these particular categories of language are referring to as they describe units. One of the really great features of this is the ability to find more information throughout the National Geologic Map database. So I can click here to go over to the NGMDB's page for the original map that described this geology. Zoom in to the same area that I was looking at here. Alternatively, I can find other publications, both geologic maps and other geoscience reports around this particular polygon by clicking on the NGMDB Geoscience Catalog button, which I can filter by and sort by the most recent publications, or perhaps by publisher of those publications, or in the case of maps, what scale those things might be published at. This will navigate me to both data that I can download and just lots of interesting reports and other information about the geology around that spot. Similarly, if you want to view just more detailed maps on the fly, you can go over to NGMDB's Map View, tiled catalog of detailed and less detailed geologic maps that's constantly being updated, where you can see the geology in scans of maps that were published across the many decades of the USGS and state geologic surveys producing those maps. And you can find your way to an individual publication and see what it had to say about, in this case, groundwater hydrology in this part of the world. One of my favorite features of this map is the ability to search for more information. If I want to find out something about particular named units, what I want to do is search while I have this source tab activated. So I'm going to look for some rocks that are in my backyard here, the Dakota. If I type in Dakota, I can see other places where this is outcropping around the western US. If I'm interested in discovering just certain types of materials, what I want to do is navigate to the geomaterial view. Maybe I'm interested in volcanoes. And I can come over here to the Yellowstone hotspot track, click on a polygon. When you have a selection active, you're always going to get these little hints for types of things that you can search for. And on geomaterial and age, those hints are going to reveal to you the taxonomy of those vocabularies. So here I can look for other lava flows, or I can look for all extrusive igneous rocks, or just all igneous rocks in general, moving up or down that taxonomy to see things that are associated with that unit that I've selected. I'm a huge fan of this, in particular for age too, as somebody who had a hard time remembering geologic histories. If I zoom into my own backyard here in Denver, I can click a polygon and see the hierarchy of the Phanerozoic coming up from these late Cretaceous rocks. Perhaps I'm interested in where dinosaur footprints might be present. And so I'm going to select the Mesozoic to see all the units that outcrop at our surface that might contain hints of that information. Thank you, and we're happy to take any questions.
Hello, everyone. My name is Don Sweetkind. I'm with the U.S. Geological Survey based out of Denver, Colorado, and I'm pleased to be part of this geologic mapping and modeling webinar, where I'll speak on construction of 3D geologic models utilizing geologic maps and subsurface data. Why do we build 3D geologic models? Well, here's an example of a study area in west central New Mexico where we have both a geologic map and a 3D volumetric geologic model. We build 3D geologic models because geologic problems are multi-dimensional. Geologic maps are the land surface representation of a full 3D volume. And however well attributed, our digital versions of traditional geologic maps are not sufficient to solve multi-dimensional problems. Digital geologic maps, however, are a good starting point
for the 3D representation of the Earth, and that's what we'll be talking about in today's presentation. So how do geologic map data inform a 3D geologic model? I'm going to use an example from the Piceance Basin in western Colorado, where I'll show you how we can convert geologic map data to XYZ input data into a 3D model. And we'll be standing near where the star is and looking to the northwest at a 3D rendition of geology. So here we are in the Piceance Basin with the oil shale rich Green River Formation dominating the upper half of our view, overlying the Paleogene Wasatch Formation and a variety of dipping Upper Cretaceous beds on the right-hand slide. And we're looking at a digital geologic map that's draped on a digital geologic model in a 3D scene. So if we add a geologic map contact from our digital geologic map, in this case the base of the Green River Formation, which is the top of the Wasatch, we can, in a GIS, we can decimate the geologic contact into a series of equally spaced points. And we can use those points to query the underlying digital elevation model and give a surface elevation to each one of those points. When we do that, we can end up with a digital file that has X and Y coordinates from the map projection and Z coordinates from the digital elevation model, and then we have an attribute that tells us which geologic map contact this is. So in this way, we've converted a digital geologic map contact to points that we can effectively bring into 3D modeling software. So in this case, the geologic map has served as input to the model. We can also think about subsurface interpretation from map data and from outcrop pattern, because geologic maps contain a wide variety of information that bears on our subsurface interpretation, including bedding orientation, measurements of the traces, and even the orientation of fold axes and faults. And geologic maps display the relationship between unit contacts and map polygons that dip at various angles and topography. And I'll show you in the example coming up here that geologists are really thinking in 3D as they map. So we're going to be standing at the upper left at the location of the star, looking to the southeast across this map view. And here we are. We happen to be above the upper parking lot of the famous Red Rocks Amphitheater on the west side of Denver, and you can see the parking lot is empty. We're quite early for our concert, which gives us a minute to think about the geology that we're seeing. And Red Rocks Amphitheater itself is enclosed and formed by conglomerates and arkoses of the Pennsylvania Fountain Formation, and across the Broad Valley we can look at hogbacks of the Dakota Sandstone and the underlying Morrison Formation, famous throughout the West for its dinosaur tracks and dinosaur bones. But if we look a while longer, we can notice that Fountain Formation outcrops progress along the mountain front to the south, and as do Cretaceous Dakota and Jurassic Morrison formations as they go off into the distance. And that map pattern is shown by the stripes of map polygons on the geologic map. But if I were to ask you to draw a profile view of what this scene might look like in the vertical dimension from what we've learned from the maps and our observations standing here, most of you might draw something like this, which has two key important features. The first being the black line, where you're drawing topography with an asymmetric hill in the center, and then you're showing geologic map units dipping from the surface down into the subsurface from right to left, or from west to east in this case. And we might differ on where exactly to put those lines, but I think many of us would come up with a diagram that looks similar to this. So there are 3D aspects to geologic field observations, and we understand a couple of things from this simple example that we've learned from a long time in geologic mapping. First is that surface map relations can be projected into the subsurface. So our surface mapping is providing us clues into the geometry of the subsurface. And the second key idea is that of superposition, and that is the simple fact that younger units overlie older units. So in this case, the oldest unit would be on the bottom, and we would get progressively younger as we move up the stratigraphic section. This is a key concept in 3D modeling because it gives us stacking order. We build these units, these models, one unit at a time, and so we need to know the relative age relationships in order to build correctly. And these surface and subsurface observations have been around for a long time, and here's an example from the first national scale geologic map of William Smith. And the geologic map on the lower left shows a series of dipping beds between Bath and Bristol in the western part of the UK, and along the cross-section line you can see the cross-section that William Smith drew is very, very similar to what we drew for the Colorado Front Range. I've flipped that cross-section around. So since that time, many geologic maps that are published come with an accompanying cross-section that contains the geologist's interpretation of what the subsurface is doing, strictly based from the geologic map patterns that have been mapped. And we can extract data from these geologic cross-sections in a very similar way to which we extracted data from the geologic contact. And here I'm showing my work copy of one of those sections in which I've drawn 4 vertical lines, and in map view these would be points where I already know the X and Y locations, and along those lines I've selected geologic formations of interest, and I can simply, using the vertical scale of the cross-section, measure off the elevation of each of the formations in the subsurface. We could do all this digitally. I'm showing an example where I've done it by hand, and I've come up with a series of elevations at a single point that are derived from cross-section information. So again, cross-sections are often part of geologic maps, and here we can derive digital data from them. And taking this to the extreme, and we'll go back to the example of the UK, where I'm showing a simplified geologic map of the UK on the left, and on the right I'm showing a network of geologic cross-sections that were built specifically to support the United Kingdom's national 3D model. And if you were to look carefully at this for a while, you could convince yourself that the geologic map patterns are represented pretty faithfully within the bulk of the geologic cross-sections. And in the lower right of the cross-section image, you can see gently dipping beds that represent the place where William Smith was drawing his cross-sections long ago. A third type of geologic information that we can use in 3D models comes from subsurface information from drill holes and borings. These can be oil and gas wells, water wells, and engineering borings. And here I'm showing a 3D rendering of subsurface data from the US Gulf Coast. We're looking from east to west across the Mississippi embayment and the Gulf Coastal Plain in south central United States. And each one of these cylinders or soda straws represents data from an individual borehole. And the colors that you see represent the top and base, or the subsurface extent of specific geologic formations that I've compiled at each borehole. And you can see that there's a satisfying regularity to where these formations exist in the subsurface. It's not random. We're measuring something that has a geologic trend. And I've put this particular visualization up on the web in a place where you can access it. You can rotate this model, zoom in and out, and at the circled numbers, there's additional information about what you're looking for. At the lower left of this slide, I've given you the URL, or if you want to take a picture of the QR code on this slide, you can look at this model directly on your phone and interact with it. So it's a way of keeping subsurface geology literally right at your fingertips. We can use borehole information to map geologic units in the subsurface. And here we're looking at a special type of map to the northeast of where I live in Golden, Colorado. and the small black dots with numbers next to them represent the subsurface intercepts of a specific geologic formation, in this case the Fox Hills sandstone. And each well then defines the top of this unit at a single location. The green lines represent elevation contours that we can interpolate through the elevation point values. So for instance, the 4,200 foot elevation contour separates 4176 and 4152 from the higher elevations of 4221 and 4265. And these contours are derived in a very similar fashion as how land surface contours might be shown on a topographic map. So what the result of this is a structure contour map that defines the subsurface unit top of the formation of interest. And it's read in the same way that a topographic map might be read, but this is a map of the subsurface. And we can zoom out and do this at a regional scale. Here we are in the Gulf Coast again. It's hard to see, but along the southern part of the slide, you can see the Louisiana coastline. At the left center of the slide, you can see a pattern of interstates, which represents the Dallas-Fort Worth area. And all of these contours are the structural top of the elevation of the Wilcox Group in the Gulf Coastal Plain. And we're mapping this in the subsurface, so it might seem that we're very far away from a 2D geologic map, but that's not so. I can bring in the geologic map polygons that represent the outcrop pattern of the Wilcox Group that are mapped at land surface in this sort of dark yellow pattern. And everywhere to the south of that outcrop, the Wilcox Group is present in the subsurface, and we map the top of that unit by structure contours. But to the northwest and northeast corners of this map, the Wilcox Group is absent. It's been removed by erosion, and units older than the Wilcox Group crop out. So in this case, we're using the digital geologic polygons from a geologic map to define the unit extent of the Wilcox and define for us where we need to define that unit in the subsurface and map it and where we don't. So again, there's an interplay between the geologic map and 3D geologic models. So I haven't told you how we build models, but we have been looking at specific elements of 3D geologic models, which include an X, Y, and a Z coordinate and a property. So we develop a network of spatially registered geologic data, but at that point it's not just connect the dots. We have to use a variety of 3D interpolation routines on our computer and add geologic rules to build our 3D volumes. And I have not explained, but there are many types of models where we can model surfaces, volumes, individual cells. We can use a data-driven approach, such as what I've described, but we can also build 3D models simply based on rules. And our friends at Seequent will be showing you an educational tool within this webinar that uses a rules-based approach to fill a 3D volume with geologic units. Our model scale and content depends on the purpose of our model, but all of our models are fundamentally predictive. They extrapolate through an incompletely sampled volume to predict the subsurface. What are 3D geologic models used for? A wide variety of things. We can build models in the natural hazards arena for looking at crustal scale fault surfaces, and they can inform 3D seismic velocity models. In the energy and minerals arena, we can use 3D models in managing our 3D data and visualizing the subsurface for reservoir and play analysis, resource assessment, and volumetrics. In water assessments, we can define the thickness and extent of groundwater aquifers. Geologic data can serve as inputs to numerical process models such as groundwater flow and transport models. And 3D models of lithology can serve as a proxy for physical properties or hydraulic properties such as hydraulic conductivity. And finally, we can understand Earth systems and do risk analysis in our geologic framework studies through the prediction of subsurface conditions and attempt to minimize unexpected geologic conditions that could be a real hazard and a real cost sink in infrastructure projects. And the 3D geologic models can be part of our planning and decision-making process. So I haven't told you how we specifically build geologic models, but I hope that I've described for you in some ways how geologic map data inform a 3D geologic model. Geologic maps and 3D models are simply complementary views of our multidimensional world. And I think digital geologic maps can be an excellent starting point to the 3D representation of the Earth. So I thank you for listening. I hope this provides an interesting extension of the discussion of 2D geologic maps that's been going on in this webinar, and I have my contact information shown here if you have questions or would like to hear more from me. Thank you.
The final segment of this webinar looks at resources that allow students to interact with 3D geological models.
Hello everyone, my name is Melissa Pereira. I work at Seequent as a Senior Technical Support Analyst for 4 years. And today I'm going to talk about how to empower students with 3D geological modeling in Visible Geology. So what is Seequent and what do we do? Seequent operates at the forefront of building a collective understanding of the Earth. We build a world-leading subsurface Earth modeling, analysis, data management, and collaboration software that connects people and data. Our geoscience and geoengineering technology is designed to transform the way our customers work and enable people to solve some of the most complex challenges of our time. We do this because it matters to every person and every action on Earth. A deeper understanding of subsurface leads to better decisions about our planet and future. We're passionate about investing in geoscientists and innovators of tomorrow because without them, there is no future for the world as we know it. Almost 30% of US geologists will retire by 2030, and that's a skills gap of 130,000 people in one country alone. Seequent has over 500 relationships with universities and academic institutions globally, and we've connected an international network of students, educators, and researchers around the globe, giving them access to our cutting-edge software and advance our collective understanding. And one of those I'm going to be talking about today is Visible Geology. So Visible Geology is a free earth science education tool. It's a browser-based, which means you don't have to download anything. We ask people to use only on their computers and laptops because it's where its performance is better. You're going to see that Visible Geology is very intuitive. It's easy to use. And something very cool about it is that we built this tool with the help of our leading video game developer. So in Visible Geology, you can build basic conceptual geological models. You can create cross sections, use stir nets, and much, much more. So students are usually learning about these concepts in 2D based cross sections and maps, stir nets, and many of them, they have difficulty visualizing that in 3D. And with Visible Geology, students can have all those concepts into 2D transformed into 3D in an interactive way, so they can master it. We have had over 100,000 users in Visible Geology since we launched it in June last year, and that's growing each day, which is amazing because we can see how excited the students are in learning more about geology, and also the teachers to have an extra interactive tool that they can teach in a more illustrative way, so then students can grasp those concepts much, much better. So today I'm going to take you through some steps of creating a geological model in Visible Geology. But before we get into that, what are geological models and why they're important? So very basic concept. Let's not dive too deep into this, but the geological models, they are 3D representations of relevant geological structures, events such as beddings, faults, folds, etc., and helpful visuals such as cross sections, core logs, and more, which could be done in visible geology. And why these are important? Because it helps students to understand real world structure from 2D to 3D, as I mentioned before, enhance their spatial skills. It helps them to understand the geological processes and principles, especially so many people that have reported that they have issues with plan maps when they're seeing that for the first time, to visualize that in 3D, what that plan map in 2D means in 3D. So having this tool that you can go from 2D to 3D super easily, it helps you to grasp those concepts much easier than trying to just visualize without any support. And helps interpreting data from the classroom learning to practical applications in geology. So building the maps in Helens, it was a little bit of fun. Oops, sorry. What I like to do when I'm building geological models in general in visible geology is to understand that that's a program for basic concepts. So what I want is to grab a general idea of what I want to build. So I want to always like collect cross sections, conceptual modeling of the area, if available. For example, it's a volcano, so I can get conceptual modelings of a volcano. So then I have, if you're not sure how the structure of inside a volcano should be, it gives you a better idea. And then of course the topography, the current topography, so then we can try to represent that the better way possible. So once you find those, you can start building something in visible geology. So I like to start with building a temporary topography. You can create custom topographies in visible geology. At this moment, you cannot edit them, but you can create as many as needed. So once I have my basic temporary topography, excuse me, to be my base, I will add my events to it. So I want to add my beds, I want to change the colors, and then I will start building my events, right? I will add my dikes and then my plutons, and then I will keep adding the more events as needed. Once those events are added, it's time to rework on your topography. As you can see, on number 1, that was the first topography that I started with. And then that one didn't represent very well what I wanted. So I kept changing the topography until I was satisfied with the results. I'm a little bit perfectionist, so at some point you just gotta like stop yourself. So the final model, I'm not 100% satisfied with that, but you just like keep going and going. So you have to find a little bit of balance with that. You just start having fun building all these different topographies, and then it's it's hard to stop sometimes. But anyways, so you start like recreating it to better like understand how you're going to be representing, and then maybe what's missing. And then one good thing about visible geology is because then you can go back. So if I go back here in the history, you can change the position of that. Maybe you want something to come before or after, so you can change that in visible geology. And the same with like maybe now that this is my final topography, I don't want my dike dipping this way, I want to like change to another direction. All that you can be doing in visible geology. So before I hand over to Lauren, I will just show you quickly how you could be doing that in visible geology. So in your history tab, there is this pencil here, and then this is where you can be changing any information that you want about your strike dip, the thickness of your dike, And once you're satisfied with that, you're going to hit apply. Sorry, I can't because my recording is blocking me, but you hit apply, that's right behind my face. And then same, like maybe you don't want the Pluton anymore, you only want to have one, so you can, after your final product, you can come back and hit the history tab, and then you can modify that. So now I'm going to hand over to Lauren, and then she'll be taking you through the lesson plan that the team at the American Geoscience Institute developed, so then you can adopt this in your classroom. Thank you, everyone.
Thank you, Melissa, for showing us the capabilities of visible geology. I now want to introduce lessons that have been developed for middle and high school students to use the program. Since Seequent became an Earth Science Week partner 2 years ago, we at AGI have worked with them to develop lessons that guide students in their use of visible geology that align with a combination of middle and high school science standards. So students can use the program to explore geological processes and see how models are used to understand those processes and geologic features. So for example, this one connects to geothermal energy. And then we have one that's open-ended in order for students to build their own geologic model with really a guide on all of the different tools that Melissa talked about within the program. And then there's a couple of site-specific lessons where Visible Geology and Seequent have pre-built those models, and students are able to explore that while also applying what they have learned about geologic features so far. So it starts with a background, so on Mount St. Helens and the Cascade Range and the tectonic activity in that area, while connecting with the next generation science standards here, as well as the skills involved in that, and as well as the Sustainable Development Goals. So these are from the United Nations and give a real-world context for learning by looking at real-world problems and how geologic processes relate to that. So what this has students do is interpret a simplified cross-section of the Mount St. Helens model to see what students have learned about geologic processes, like applying the law of superposition and looking at the events within this diagram. And so this was made from that model within Visible Geology. So students start here interpreting that and then are prompted to talk about how confident they are in their answers, consider where they had difficulties in placing those processes, just like they would if they were looking at a diagram of Mount St. Helens. But here, they can now then go into the Visible Geology program and use the instructions here, as well as in the other lessons, in order to use the tools to attempt to rebuild that. And in doing so, they can understand more the interpretation of models by building one themselves and using those tools. And as Melissa mentioned, because it has a game-like feel to it because of the way that Visible Geology was designed, a lot of students actually find this very intuitive to use those tools and manipulate the layers within the models. So the students are building the model really as a stepwise function and coming back and revisiting their work and seeing if that's helping to improve their interpretation, because they're really learning and focusing on how models can be used to understand features, which can then be translated into geologic maps as well. So the goal here was not to get them to build a perfect model or even recreate the detailed model, as Melissa showed, that has a lot of features on it, but in order to just get to understand how models are made. And then we always end with a synthesis question that has that real world component there. So again, going back to the topic of sustainability, looking at geothermal energy sources around volcanoes and considering the geology of the area. And even interpretation of a geologic map is going to tell you about building infrastructure in that area. So we hope that you consider using these lessons to get your students to really engage with the material and translate this to geologic maps. Thank you so much for joining our webinar today. We hope that you enjoyed the resources and information that was shared. If you have any questions about Earth Science Week, Geologic Map Day, or this webinar, please contact us at info@earthsciweek.org.